say, do what you can between now and then to just start getting ready for final, right? The comprehension questions are up there, start working on those. Particularly, if you did not do well on that first test, as you're going through those comprehensive questions, if something doesn't make sense, or you're not really sure how to answer it, you know, make sure you ask me so we can get all that clarified, you know, so you can start working on that stuff. Otherwise, oh, and you got your worksheet to kind of think about getting done. I can't remember when I made that due, but it's kind of soon, right?
Monday.
And then your case study, you know, so be thinking about getting those done. Remember that GI worksheet, it's not hard, but it's gonna take you a while to do it, okay? You gotta watch a video, answer questions, watch a video, answer questions. Keep it short and sweet, okay? Don't give me lots of wordy stuff. If I left you that much space, that's because that's what you should write in there. If I left you a line, that's what you should do, okay? You don't need to all of a sudden, if I left you a line to put your answer in, write me a paragraph, okay? Keep it short and sweet. Okay, questions, comments, issues? You guys doing anything for Thanksgiving? You cooking? Yeah, you're actually cooking. You're cooking.
Oh, not me.
No, okay. Wow, okay. All right. I'm like, I'm coming over if you're cooking. All right. Okay, we ready? Ready to do it? Okay, all right. Let me pull up Tempo. Okay, so basically we're going to start back at the corpuscle and we're going to work our way through the nephron and we're going to start doing details along the way here. We're going to spend most of this lecture talking about the pressures that influence whether a filtrate is formed or not, and then we'll look and see how you regulate that process and what would happen if you couldn't produce a filtrate. So we're going to spend quite a bit of time here. We're going to be looking at these pressures again. So if you felt like you didn't learn them well in blood vessels and circulation, well, you're going to see them again. And it's the same basic idea with a couple little differences, but same basic idea. And we're going to go over it in a fair amount of detail. So if you didn't understand it before, hopefully by the time we're done with today, you'll understand it now, okay? Make sure you ask questions if not. We'll say a little bit about the PCT, and then we'll spend the next kind of amount of time at the loop of Henle, and then talking about hormones at the DCT and the collecting duct, and we'll just kind of see how far we get with that today. Okay, so here, we're gonna start by saying, what are the different forces that determine, are we going to produce a filtrate or not? So we're gonna draw the corpuscle, and we're gonna draw blood coming in and out of the glomerulus and start looking at pressures here. So let's do Bowman's capsule. And then coming out of Bowman's capsule, we have the PCT. And so this thing right here is Bowman's capsule or the glomerular capsule. And then we're going to draw blood vessel, bringing blood into and out of the glomerulus. So we've got the afferent arterial bringing blood in, and I'm going to abbreviate this as AA. Okay, afferent arterial. And then we've got the glomerulus here. And remember, it really would be a tuft of capillaries. I'm just going to draw it as a backward C though. And then blood coming out of the glomerulus is taken away through the efferent arteriole, and I'm just gonna abbreviate it as EA. Okay? So afferent arteriole is bringing blood in. This right here is the glomerulus, which remember is capillaries. And then leaving, we've got the efferent arteriole. And then from there, we would go into the peritubular capillaries, and we're not gonna worry about those, but I'll just write it up here. Okay, so that's where the blood would go next, wrapping around the tubule. Okay, so when we looked at a regular old systemic capillary, we said that at the arterial end of a regular old systemic capillary, the blood pressure in that capillary at the arterial end forced water and solutes out. And we said that when you look at a regular old systemic capillary, the pressure in that capillary is not very high, and it doesn't change whether the ventricles are in systole or diastole. We're so far removed from the heart that pressure stays pretty constant at a systemic capillary, and it's relatively low. So at the arterial end of a systemic capillary, it's about 35 millimeters of mercury. It's pretty low, okay? But it's enough to force water and solutes out. And we called that pressure inside a regular old systemic capillary, we called it a capillary hydrostatic pressure. And that's because hydrostatic pressures are just where you have something pushing against something else. That's a hydrostatic pressure. So if I'm pushing against this, I'm exerting a pressure on this. That's a hydrostatic pressure. When you look at blood inside of a blood vessel, like blood inside of a capillary, your blood is exerting a pressure against that capillary wall. That's why that's a hydrostatic pressure. And we have the same thing in here. We have pressure due to the blood pushing against the walls of the glomerulus, exerting a hydrostatic pressure. So again, the blood pressure in this capillary just happens to be called the glomerulus, but it's still just blood pressure in a capillary, is forcing water and solutes to come out, okay? And that is a hydrostatic pressure. Now here, instead of calling that hydrostatic pressure in our blood vessels, instead of calling it a capillary hydrostatic pressure, like we did at a regular old capillary, here, since the capillary has a name, it's called the glomerulus, we're going to call this pressure the glomerular hydrostatic pressure. It's still just the blood pressure in a capillary, okay? It's just in this capillary right here. So if we look at that, okay, and it would go this direction too. We'll put it both ways. So that's your glomerular hydrostatic pressure. Glomerular hydrostatic pressure. Put it up here. So we'll put pressures affecting production of a filtrate. So this is what determines whether we produce a filtrate that starts traveling through the PCT, the leukopedaling, the DCT, or not, okay? So we've got hydrostatic pressures, that is one, hydrostatic pressures. And again, a hydrostatic pressure is just something pushing against something else. And the major driving force for producing a filtrate, the major driving force that's going to cause water and solutes to come out, is that right there, the glomerular hydrostatic pressure. Okay, so that's glomerular hydrostatic pressure. It basically is just the blood pressure in the glomerulus. That's what that is. Okay. And that is going to, I'm going to put a plus sign here because it's going to favor forming a filtrate. I'm going to put a plus filtrate. It favors forming a filtrate. Now, We said when you look at a regular old systemic capillary, the blood pressure or the capillary hydrostatic pressure at the arterial end was about 35 millimeters of mercury. And if we look at the blood pressure in the glomerulus, it's a little bit higher than 35 millimeters of mercury. So the first thing we want to say is why? Why is the blood pressure in here higher than in a regular old systemic capillary? And it has to do with the fact that if you look at a regular old systemic capillary, you have an arterial bringing blood in, but what takes blood out of a regular old capillary? What is it? A venule, okay? That's not what we have here, okay? What we have here is an afferent arterial bringing blood in and an efferent arterial taking blood out. And when you look at these arterioles, there is smooth muscle in the wall of those arterioles. And if you remember, when you look at the smooth muscle in the wall of most of your blood vessels, not all, because like capillaries don't have smooth muscle in the wall, but most blood vessels, if there's smooth muscle in the wall, it is innervated at a baseline level by the sympathetic nervous system. There's always some amount of sympathetic innervation at the smooth muscle in the wall of a blood vessel all the time. That's your autonomic tone, or technically it's called vasomotor tone, because you're talking about a blood vessel. And that just causes your blood vessels to always be slightly vasoconstricted. And that helps set up pressure, helps to set up blood pressure so blood can move. It's also important because what it means is we can either increase that sympathetic activity and make that blood vessel constrict more and make pressure go up, or we could make that sympathetic activity decrease because it's not at zero at rest, it's something at rest. So that means we can make it go up or we can make it go down, and thus we can change it, okay? We can make it vasoconstrict more or vasodilate more. Now, back to this, okay? That's just kind of a review from before. There are no parasympathetic fibers at the smooth muscle of blood vessels. Blood vessels are not duly innervated like the heart. They're sympathetic there, but not parasympathetic there. Okay. Back to this. When you look at the smooth muscle in the wall of these arterioles, like any other arteriole, they are always slightly vasoconstricted. And the other thing is, when you look at these two diameters at a resting state, let's write this over here. At rest, the diameter of the afferent arteriole is slightly larger than the diameter of the efferent arteriole. Okay? That's just the way it is at rest. Now we can change that, and we'll talk about how and why you would change that in a little bit, but that's what it is. And because of that, blood, let's think about it kind of like this. Blood comes into the glomerulus fairly easily, but now when it tries to leave, it's got more resistance trying to leave. It's a little bit harder to leave because the diameter is smaller. It's harder to get out. And because of that, it causes the pressure in the glomerulus to pop up a little bit. Okay? That's why the pressure in the glomerulus is higher than a regular old capillary, because you don't have that going on in a regular old capillary. Blood comes in through an arteriole, it leaves through a venule. It's not dealing with these diameters being a bit different and having that increased resistance. So this is why the glomerular hydrostatic pressure is higher than a regular old systemic capillary hydrostatic pressure at its arterial end. Okay. All right, now, the other thing that's different here is when we looked at a regular old systemic capillary and the capillary hydrostatic pressure forced water and solutes out of that blood, out of the capillary, the water and solutes went into the interstitial fluid, which is basically kind of like an ocean for little solutes and little water molecules coming out of the bloodstream. But that's not what's happening here. The water and solutes don't go into the interstitial fluid. That would be out here. That would be the peritubular fluid. Instead, the water and solutes go into this confined capsule, into a confined space. they go into the capsular space of Bowman's capsule. They go into the hollow place of this capsule. And so as the water and solutes come out, it runs into the wall of the capsule, right? And because the water and solutes, when it comes out, it runs into the wall of the capsule is exerting a hydrostatic force that's basically forcing the water and solutes right back in, right? So we didn't have that out in the interstitial fluid. The water and solutes came out and it was like an ocean. They just kind of diffused within this vast interstitial fluid. But we don't have that here, okay? So that means that we have another hydrostatic pressure here that we didn't have at a regular old systemic capillary. And that second hydrostatic pressure is called the capsular hydrostatic pressure. The pressure exerted by the capsule. So as the water and solutes come out, the capsule then is going to exert, let's put it down here. The capsule is going to exert an opposing force and force the water and solutes to go back in. So if we come up here, we're going to say the capsular hydrostatic pressure, or the pressure exerted by the capsule, Bowman's capsule, the glomerular capsule, whatever you want to refer to that. This is going to be opposing the formation of a filtrate because it's forcing the water and solutes right back into the glomerulus. So now we have two hydrostatic pressures that oppose one another. And in a regular old capillary, we didn't have that. We just had the capillary hydrostatic pressure favoring filtration, and that was it, end of story. So here we have to add up these two numbers to see what the net effect is. What is the net effect based on hydrostatic pressures? What are we going to get just based on hydrostatic pressures? Is the glomerular hydrostatic pressure going to be greater than the capsular so that we do produce a filtrate? Or will it be the opposite? Will the capsule exert a greater pressure than the blood pressure in the glomerulus and we don't produce a filtrate? So here we're going to add these two up and we get our net hydrostatic pressure. So when we add these up, we take our glomerular hydrostatic pressure, which is favoring a filtrate. And from that, we're going to subtract the pressure exerted by the capsule, and we're subtracting it because those forces oppose one another. Now, if we take real numbers and put them in, the blood pressure in the glomerulus, or the glomerular hydrostatic pressure, that's about 50 millimeters of mercury. Remember, we said it's a little bit higher than a regular old systemic capillary's pressure, which was about 35. Now, that number can obviously change, but that's kind of typical for what it is at rest. And then, assuming that our kidney's working fine, we don't have any infection, our capsules are nice and intact, they're not damaged, then that capsule exerts a small pressure, but it's still a pressure that opposes this one. And that number is about 15 millimeters of mercury. So it's not very big, but it does oppose forming a filtrate. When we add up these two numbers, we get a net hydrostatic pressure, and now we're back to that 35 millimeters of mercury again. What this says is when we add up just hydrostatic pressures and only hydrostatic pressures, it says that we will get a net hydrostatic pressure that's 35 millimeters of mercury. It's not very big, but it is positive. And because it's positive, that tells us that yes, based on these two forces, we will produce a filtrate. Okay, questions on that part of this story? Okay, but now we also have to think about the fact that when water and solutes come out, let's put that here, when water and solutes come out, not all solutes come out, right? Only solutes that are small enough come out. There are some things that are still in the glomerulus. Things like a little bit of water still in there. Not all the water came out. Cells are in there, but more importantly, plasma proteins are in there. There's still, all of our plasma proteins should still be in the glomerulus. And because those plasma proteins are in here, that sets up an osmotic pressure that's going to try to draw water right back in. Osmosis says that water will move towards an area of high solutes. Now, when we look at the osmotic pressure going on here, we're not looking at total solutes. And that's why we don't look at just osmotic pressure. What we look at instead is called BCOP. It's not osmotic pressure, it's blood colloid osmotic pressure. This is saying, where is water going to go based on a high concentration of plasma proteins? Not total solutes, but just plasma proteins. And when we look at where the plasma proteins are, they should all be in the blood because they should have been too big to leave. We've got most of our water outside at this point. And so now we're gonna see an area where we have high water out here, low water in here. We should have no plasma proteins out here. Or up here you'll see it referred to as suspended proteins. Okay, same difference. And in here, we should have a high concentration of suspended or plasma proteins. And based on that force right there, just osmosis, where will water go based on osmosis? Water's gonna move from high water, low solutes, not all solutes, low plasma proteins, to an area of low water, high plasma proteins. This force is our BCOP. BCOP is gonna draw some of that water right back into the glomerulus. So if we look at our BCOP, this is the driving force for water to move towards a high concentration, not of all solutes. We're not talking about osmotic pressure. We're talking about blood colloid osmotic pressure. So it's for water to move towards a high concentration of suspended proteins or plasma proteins. And again, assuming that everything is working properly, this will oppose filtration because this is going to drive water right back in to the glomerulus. Now, that number could change, okay? If, for example, the area that makes these plasma proteins, if that area is not working properly and we're not making plasma proteins, then that driving force would be much lower, okay? And where we make most of these plasma proteins is at the liver. So let's say you have a patient who has been a heavy drinker for most of their life. They're starting to have liver damage, then their liver's not gonna be making plasma proteins the way that it should. They'll still make plasma proteins, but they won't be making nearly as many as they should be making, which then means that there won't be as many plasma proteins in the blood if the liver is not doing what it should be doing. And if there are less plasma proteins in here, then the driving force for water to be drawn out back into the blood will be less if there are less plasma proteins. So that means that even though we might still get water coming back in, we might not get as much. And if we really have problems with our liver and those plasma proteins are really low, then we might not be drawing water back in at all, potentially. And that, again, could be a big, big problem, okay? Then you start having problems with regulating your blood volume, regulating blood pressure. People that have, that are chronic drinkers and have liver damage, they often look very puffy, very swollen, a lot of edema. And if you think out at your systemic capillaries, if you have low BCOP out of the systemic capillary, then that water just sits in the interstitial fluid and doesn't get drawn back in. And that's why those people tend to look very swollen, very puffy a lot of the times. Okay, so you've got these forces that are all working together, okay? So then what we want to do is we want to add everything up and say, when you take all of this into account, do we produce a filtrate or not? Okay? So if we take all of this stuff, then we're looking at what's called filtration pressure. So filtration pressure is going to take into account BCOP, glomerular hydrostatic pressure, capillary hydrostatic pressure, and add them all up. So filtration pressure. Okay, so again, we're saying, are we going to produce a filtrate or not? The driving force to produce a filtrate is this number right here, our net hydrostatic pressure. So we've got our net hydrostatic pressure. This is a positive number. And again, this number takes into account these two. Okay? We could, if we wanted to, we could write the whole thing out and say glomerular hydrostatic pressure minus capillary hydrostatic pressure. Then we'll subtract this number. Okay? So instead of writing that all out again, we just say, let's just take our net hydrostatic pressure. Okay? Net hydrostatic pressure, which is these two numbers subtracted from one another. We're going to subtract from our net hydrostatic pressure this number, BCOP, and we subtract it because it opposes filtration. So we're going to subtract from that BCOP, and again, we could all so again, if we take real numbers, we already calculated our net hydrostatic pressure is 35, that's these two numbers. So we've got 35 millimeters of mercury. Like we saw before, assuming that our liver is making plasma proteins like it should, the BCOP should be a pretty constant number, okay? Shouldn't really change, again, unless the liver's not doing what it should be doing, then that number would be smaller, okay? If the driving force is less, that number would be smaller. And that number, at a normal, everything working okay at a resting state, is 25 millimeters of mercury. So that gives us a filtration pressure of 10 millimeters of mercury. And again, that's a pretty small number. 10 millimeters of mercury is not a lot, but the critical thing is it's positive, okay? It's a positive number. The fact that that's a positive number, will we produce a filtrate or not? Yes or no?
Yes.
Yes, so this favors filtration or favors the formation of a filtrate. You can say it either way. Favors filtration or favors the formation of a filtrate. Now, the thing to keep in mind though is there will be times when that number becomes 0. There will be times when that number is a negative number. So let's say this number was 0. Okay, let's just say it was 0. If that number is 0, then what does that mean? If our filtration pressure is 0, will we produce a filtrate? This has become 0. Will we produce a filtrate? No. And if we don't produce a filtrate, then that means we won't be producing what very shortly thereafter?
Urine.
Urine, okay? So if we don't have a filtrate, we can't produce urine, okay? And is that a problem?
Yes.
Possibly, okay? Depends on how long that goes on for. For short periods of time, it's actually fine. If you are in strong sympathetic mode, you very well will not produce any filtrate. And again, that's okay for short periods of time. Remember, I've said this many times now, we never evolved to be in sympathetic mode as often or as long as we are. We put ourselves in that stressful state way too much and way too often. Our body was never designed for that. It was designed to fight or flee and then be done with it. So if you're not producing filtrate in urine for short periods of time, it's fine. But if you're not producing a filtrate in urine for extended periods of time, that's very, very bad. It's bad because one, all those organic wastes are still in your bloodstream, traveling around, affecting anything it comes in contact with. It's bad because through your kidneys is where you're going to homeostatically regulate things like sodium levels, potassium levels, calcium levels. And if those levels stay out of homeostasis for too long, you could end up dead. Your urinary system, through producing filtrate in urine, is going to help regulate your blood volume, your blood osmolarity, how thick your blood is, your blood pressure. And so if you're not producing a filtrate, then you certainly can't regulate those parameters, at least through the kidneys. So you're going to have to regulate them other ways. And you never want to rely on just one way, because that other way might get wiped out too. And then you're going to die pretty quickly at that point. We're also going to see that the urinary system is a major system with the respiratory system to regulate blood pH. And again, we don't want to start wiping out a whole system because in this case, we're not producing a filtrate. So short periods of time, it's actually fine. Extended periods of time or too often, not so good. So then the question is, what number do we want to look at? Because this number could go to 0 and it'd be fine. We just don't want it there too often or too long. So the number we really want to be looking at is called the glomerular filtration rate. That's the number we really want to look at, because this is saying how much filtrate are we producing over time. That's what this number is. Over time, are we producing enough filtrate? That's your glomerular filtration rate. So this says that you're producing a certain amount of filtrate every minute, okay, over time. And that number should be about 125 mils of filtrate per minute. If you think about that, that's actually a lot, okay? 125 mils per minute is pretty, cranking it out pretty good. And again, if you look over the course of a whole day, because each kidney has about 1.25 million nephrons and million glomeruli per kidney. So that means if you look over the course of a whole day at all of your glomeruli, you are producing about 48 gallons of filtrate a day, or 180 liters of filtrate a day. And obviously we're not urinating that, okay? We're not urinating that much. And we said that's because of all this filtrate we produce right here at the corpuscle. 99% of everything that we produce, 99% of this 180 liters has to get reabsorbed back into the bloodstream as that filtrate travels through the PCT, the loop of Henle, the DCT, the collecting duct. Once that filtrate exits the collecting duct, it is urine and we can't do anything with it anymore. So we have a very short period of time, PCT, loop of Henle, DCT, collecting duct, to be reabsorbing 99% of everything we just formed right here. Okay. Now, before we get into reabsorption and secretion again, we just want to say, if this number is so important, if it's so important to keep glomerular filtration rate pretty constant most of the time, how do we regulate it? Okay. Now, what we've kind of seen with other systems up to this point is if something goes out of homeostasis, like carbon dioxide levels, or oxygen levels, or blood pressure, what we've seen is that the nervous system kind of kicks in and helps to maintain homeostasis, like sympathetic activity goes up, parasympathetic activity goes down, that causes heart rate to go up. Heart rate goes up, causes cardiac output to go up, and we can get oxygen levels and blood pressure to go up that way. So typically what we've seen this quarter is to get cardiac muscle, smooth muscle, to do things, to get various parameters to go up or down, back into homeostasis, the autonomic nervous system gets involved. But that's not what we're gonna see here, okay? When we look at cardiac reflexes, we've got the autonomic nervous system, sympathetic and parasympathetic. When we look at changing how vasoconstricted or vasodilated our blood vessels are, we did vasomotor reflexes where we dealt with just sympathetic activity. When we looked at changing respiratory rate, we didn't use the autonomic nervous system, but we still used the nervous system to increase or decrease respiratory rate. Not at the kidneys though. At the kidneys, we're going to see that the kidneys are gonna try to fix it themselves first. And then if that doesn't work, so let's call this by its name. At the kidneys, we're going to do autoregulation or intrinsic regulation. The first kind of line of defense to try to keep glomerular filtration rate constant is going to be every single glomerulus with its corresponding arterioles is going to do autoregulation or intrinsic regulation to try to maintain its own glomerular filtration rate, with the idea being if every single glomeruli, and we've got a little over 1 million per kidney, if every single glomeruli with its arterioles regulates its own GFR, and they're all doing that, all a little over 1 million of them, then the sum total should be 125 mils per minute. And that works a lot of the times. But if there's a bigger problem, okay, remember autoregulation or intrinsic regulation only works locally. It's only gonna work right here. So again, every single glomeruli with its arterioles is gonna do things, and we'll see what they do. It's gonna do things, and every single glomeruli with its arterioles will do its own thing so that the sum total GFR stays constant, okay? That's working on a local level. What happens at this glomeruli might be different from what happens at this glomeruli, might be different from this glomeruli. But they're all trying to maintain their own little individual filtration rates, so that when you add up all the individual filtration rates, the sum total is where it should be. If that can't be achieved, if we can't fix it locally, that's when we're gonna start to get hormones involved. Not the autonomic nervous system, hormones involved. If there's a problem where individual glomeruli can't fix their own filtration rate, then it's usually a problem on a systemic or a body-wide level. It's usually some problem with blood pressure throughout the whole body, not just right here, but throughout the whole body. And that's when hormones come in to try to fix the big problem so that we can fix the problem right here. Okay, we're gonna walk through that. That's when we're gonna see this renin-angiotensin system come into play. Okay. Then we'll say a couple things about how the autonomic nervous system, the sympathetic division of the autonomic nervous system, can come in and basically shut it all down. So, the autonomic nervous system, so far, we've seen always involved in trying to maintain homeostasis. Here, the sympathetic division of the autonomic nervous system is not going to try to maintain GFR. It can regulate GFR, but it's not going to try to homeostatically maintain it. What it's going to do is come in and override autoregulation and shut the whole thing down. And we'll see how it does that and why it would do that. Okay? So if I ask you on a test, does the autonomic nervous system help to regulate GFR. You'll say, yeah, it helps to regulate it. It just doesn't help to keep it within homeostatic range. What it'll do is come in and shut everything down. It regulates it, but it's not trying to keep it in homeostatic range like we typically see the autonomic nervous system do. Okay, so we're gonna walk through each of these, okay? And again, this is where we're spending the bulk of our time today, is here, right here. So before I start walking through this, questions, comments, issues, clarifications? We're going to start with autoregulation. So again, autoregulation happens locally. So what's happening at this glomeruli with these arterioles might be different from what's happening at the glomeruli and the arterioles right beside this one. They all will be doing their own thing independent of one another. It's kind of like when we talked about those pre-capillary sphincters down at the level of a regular old systemic capillary, how that regulated blood flow. Same idea. We're not going to use the nervous system. We're not going to use the endocrine system. Everything's going to work at one particular glomeruli independent of what's going on at another glomeruli. I'm going to erase this and we're going to start walking our way through this. Okay, so we're going to say if GFR starts to drop, that's where we're going to start. So let's see, let's do blue. I say autoregulation. Again, autoregulation does not use the nervous system, does not use the endocrine system. It works on local levels, not body-wide levels, not systemic levels. So this is local control. So we're looking at one particular glomerulus, and you would see similar things happening at all the other glomeruli, but everyone would be controlling its own individual filtration rate. Okay, so at this glomerulus, let's say if here, glomerular filtration rate, and I'm going to put here locally, okay, so that we keep in mind we're looking at one particular area. The glomerular filtration rate at one particular glomerulus, if it started to drop, what will we try to do to fix it? Kidneys are going to do autoregulation first. Now, this is kind of how I walk my way through thinking about this, okay? I come over here and I say, if my filtration rate is dropping at this glomerulus, okay? The filtration rate's dropping here. It's not necessarily true, but it's probably, I'm going to put probably, because our glomerular hydrostatic pressure here is a little bit too high or a little bit too low. If we're producing a bit too little filtrate here, is it's probably because our glomerular hydrostatic pressure, the driving force for filtration, is probably a little too high or a little too low. Let me say it again. If we're producing a bit too little filtrate right here, it's probably because the pressure inside of here is a little too high or a little too low.
Too low.
It's probably a little too low, right? This is the driving force. So if it's a little too low, there's not enough force forcing water and solutes out. So you're getting less coming out, okay? It's not always going to be true, but it's typically true. So it's probably because our glomerular hydrostatic pressure has dropped a little bit. And we're talking, when we're doing autoregulation, we're really talking small little changes, okay? And this is always happening. If you look at your little over 1 million glomeruli right now, they are all adjusting their local glomerular filtration rate right this second. They're all just bouncing around a little bit up, a little bit down, a little bit up, a little bit down. They're constantly just bouncing around fixing this, okay? So we go with that assumption, okay? We go with this assumption. So if that's the assumption, then to correct with autoregulation, we can, let's see, here I want to say this, we can do a couple things. We can increase or decrease the diameter of our afferent arteriole, or we could increase or decrease the diameter of our efferent arteriole, or we could do both. We could increase or decrease the diameter of our afferent, and we could increase or decrease the diameter of our efferent. Now, we'll fill in the arrows in a second. So we could do either of these things or both, okay? And the net effect of doing this is that we want our glomerular hydrostatic pressure to come up, okay? So that we get our glomerular hydrostatic pressure to come up. And if our glomerular hydrostatic pressure, again, locally, just at this one glomerulus, okay? If that comes up, then that should make our glomerular filtration rate at this glomeruli, I'm gonna put locally, come back up to range. So now let's just think about how the arrows would have to go to make this happen. Okay? So we want, remember at rest, there's smooth muscle and the wall of these arterioles is always slightly contracted. At rest, the diameter of our afferent is bigger than the diameter of our efferent, okay? So let's say that we're gonna just change the afferent, let's start there. So we're gonna leave the efferent where it is, okay, whatever its diameter is, we're gonna leave it. And if we wanna make the pressure in this glomerulus go up, would we wanna make, so think about down here, kind of like your kitchen faucet. Would we want to open the afferent arteriole up so there's less resistance and blood can come in easier? Or do we want to crank it down so it's harder for the blood to get through here and come into the glomerulus? We want to open it up, okay? So when we're down at these really small levels like this, just like when we looked at the precapillary sphincter, I always think about kitchen faucets. When I'm thinking about systemically, and I'm thinking about slightly larger blood vessels, I think about the tube of toothpaste, right? And that's how I keep it straight in my head, because this used to confuse me so bad. Because in one situation, you do one thing, and the other situation, you do the opposite, right? So let's just back up for a second. If we were thinking systemically throughout the whole body, and if I said systemically, your blood pressure was too low throughout the whole body, we would say, well, you would have the sympathetic division of the autonomic nervous system increase its activity. You would make blood vessels throughout your body vasoconstrict, like a tube of toothpaste, and blood pressure would go up and blood would move faster, right? That's within limits, because if you cause the vasoconstriction to happen too much, then if you crank it down too much, then blood can't move through. But we're saying it's like a tube of toothpaste, you give a little squeeze and there it goes, okay? But down here, because these vessels are so tiny, they're already tiny. If we crank that down, the resistance will be so great that blood can't move through here. And that's why down here, I do my kitchen faucet. Down here, if I want blood to come into the glomerulus, I gotta open this up and decrease the resistance. So I open it up by vasodilating it, right? I increase the diameter. And that's how I keep it straight in my head, okay? Otherwise, it's confusing, because you have to think about the length of the blood vessel, you have to think about how much resistance, how much turbulence. There's a whole big complicated formula that goes into it. And I just avoid that by thinking about those two scenarios. And I think if I'm down at the level, right as I'm going into a capillary, it's my kitchen faucet. And if I'm anywhere else, it's my tube of toothpaste, okay? So here, if I want the pressure in the glomerulus to go up and I'm leaving that diameter where it was, this diameter has to get a little bit bigger, okay? So I have to make the diameter of my afferent arterial increase. Or I could leave the afferent arterial's diameter where it was, blood's coming into the glomerulus, and now to make the pressure in the glomerulus pop up a little bit, I could do what to my efferent arterial's diameter. So blood comes in, we're not changing this part, blood comes in, and now to make the pressure pop up, am I gonna make it easier to leave or harder to leave? Harder to leave, so that means I'm gonna decrease the diameter of my efferent. Or I could do both. I could increase the diameter of my afferent, blood comes into the glomerulus, make it harder to leave, pressure pops up a little bit. And again, we're really talking about tiny little changes here, right? Tiny little changes. This is not under the influence of the autonomic nervous system. We're not changing sympathetic activity down here, okay? All we're doing is basically changing how much contractility is happening. We're changing how much calcium is in those cells, okay? So if we allow more calcium into these smooth muscle cells, they will contract with a greater force and they'll clamp down. If we allow less calcium into these smooth muscle cells, they will contract with a lesser force, they'll open up, okay? So it's not sympathetic activity we're changing down here. We're not altering the nervous system down here, okay? It's all happening locally, okay? It's all happening locally. So if you look at these smooth muscle cells in here, they've got little receptors that detect pressure, and then they will adjust accordingly. We don't need the nervous system. We don't have to send in information to the brain. That's not what we're doing here. Okay, so that's basically autoregulation. And to do the flip, you just flip your arrows, okay? So if your glomerular filtration rate locally is a little too high, we're gonna say that's probably because the glomerular hydrostatic pressure is a little too high, and we wanna lower it, and we just flip our arrows. Questions on autoregulation. So again, this is working most of the time, okay? Right now, all of your glomeruli are adjusting their arterioles diameters a little bit here, a little bit there. Everyone's doing it independent of the other so that the net effect is we keep GFR at 125 mils per minute. Now, okay, now, if this doesn't work, okay, if this can't correct the problem, then we have to get, if this can't correct the problem, it's probably because we have a problem systemically, okay? It's not just that, oh, our pressure in here is a little too high, a little too low, we'll alter the diameters. There's a problem systemically, and autoregulation can't fix it. Now we're gonna start to see hormones playing a role, okay? So what we're gonna do is we're gonna walk through this renin-angiotensin system, okay? We're gonna walk through this. We're gonna talk about these hormones afterwards, AMP and BMP. But we're gonna walk through this system. We're gonna talk about this stuff here. And I'm gonna use this as a reference. Okay, just leave this up while I'm talking about it. So just to give you some context, what we're looking at here, this is saying, if we have low systemic blood pressure, okay? This is just saying that if we have low systemic blood pressure, a variety of things will try to correct this problem. First thing that will happen is autoregulation, okay, is gonna try to correct it. If that can't correct the problem, then we're gonna start to see hormones playing a role, and we might even get some neural activity happening here. We're gonna be walking through this green section here. Okay. All right, so I'm going to erase all of this. Okay. So on your final, absolutely, I'm gonna ask you a question about the renin-angiotensin system. And I'm gonna say, renin-angiotensin system, and then start asking questions about it, okay? It's gonna be at least 5 points, if not 10 points. It's gonna be a lot of points, okay? You must know this, okay? When I have former students graduate from nursing and come back to me, they always say, we had to know that renin-angiotensin system. I'm so glad you taught that. It's gonna pop up on all kinds of things, okay? You've got to know this system. All right, so I'm gonna do it like this. The renin-angiotensin system. You'll also see it called the RAS. You'll also see it called the RAS. Now, to get this system started, we need a stimulus, okay? Because this is just gonna be extrinsic regulation using the endocrine system instead of the nervous system. But it's just a homeostatic mechanism like we talked about kind of all quarter, okay? And earlier in the quarter, we did cardiac reflexes, vasomotor reflexes. We changed the autonomic nervous system. Here, we're gonna be working mostly through hormones, okay? But same basic idea. Okay. So this is saying, if autoregulation can't fix the problem, okay, then it's probably an issue with blood pressure systemically. It's not a problem with just the pressure in one glomerulus. It's a problem with throughout the whole body, blood pressure is too high or too low. For this system, blood pressure's too low. That's what this system is triggered by. So again, if the problem systemically is that your blood pressure's too high or too low, autoregulation can't fix the problem, okay? Because even though you alter your arterial diameters, you've got a bigger problem with blood pressure that just can't be fixed by altering little arterioles, okay? You just can't fix it that way. So here we're gonna say stimulus. Now, there's lots of different stimuli that can trigger this system, okay? I'm gonna keep it as general and as inclusive as possible, but I'm gonna show you a slide that looks at other very specific stimuli that could trigger this, okay? So kind of based on what we were just talking about, I'm gonna say, if our glomerular filtration rate drops and it can't be corrected through autoregulation. So if our glomerular filtration rate drops and we can't fix it the way that we were just looking at, okay, then this system can be triggered. And I'm gonna add one other thing in here to make it really inclusive. If GFR drops and it can't be corrected through autoregulation because our systemic blood pressure is too low, then definitely this system's gonna get triggered. Okay? So if your systemic blood pressure is low and it's not quickly corrected through like a cardiac reflex by making your heart rate go up, or your systemic blood pressure drops and it's not quickly corrected by your blood vessels vasoconstricting, if your blood pressure stays low and it's not corrected quickly with the nervous system, then that tends to be when hormones get involved, okay? So if I were to sit down and then stand up real fast, my blood pressure will drop. This system's not gonna get activated because of that. It's too quick. It'll be corrected too quick. But if I have a problem, some other bigger problem at play, and my systemic blood pressure is staying low for hours, days, this system's gonna be at play, okay? But again, if I just sit down and stand up and my blood pressure drops real quick, this system takes too long to get started. It will already be corrected before we can even get this system started. And it would be corrected by just my heart beating faster, okay? That would fix my blood pressure like that. All right, so this is kind of the general stimulus. So on your test, if I say, what's the stimulus that will trigger this? You could say a drop in systemic blood pressure and leave it at that. That would be fine. If you say a drop in GFR, I need you to clarify it a little bit, okay? So if you want to just cover yourself, just say a drop in systemic blood pressure. Okay? Now, there's other individual stimuli that can trigger this system too, and that's what you see here, okay? So a few other things here. Now, where are we gonna start with all this? Okay. What's gonna start this is, this stimulus here is gonna cause the juxtaglomerular complex. Okay? Juxtaglomerular complex. Sometimes instead of a C, you'll see an A, and that would be apparatus. Remember, we mentioned these cells last time. I said this was a group of cells that were associated with the DCT, and in this group of cells, there are endocrine cells that make EPO, there's endocrine cells that make TPO in there, and we're gonna look at an enzyme that this group of cells make, okay? Not a hormone yet, an enzyme. So, a drop in systemic blood pressure that's not corrected quickly, that will be the stimulus that causes these cells, okay, I'm gonna put in parentheses, these are cells. Juxtaglomerular complex is a group of cells. It's gonna make an enzyme called renin. Okay, you must know the name of that enzyme, and you must know that it comes from those cells. And you must know that those cells will make that enzyme under certain stimuli, like a drop in systemic blood pressure. Okay, so what is this enzyme gonna do? Okay, these chemical reactions are in here, but I want you to know them. Okay, so I'm gonna write them on the board. Okay, enzymes catalyze reactions. That's what enzymes do. Okay, and so this enzyme is going to, I'm gonna put here, chemical reactions. This is how I worded on the test. So we're gonna have this molecule called angiotensinogen. Yep, you need to know this. Angiotensinogen. What I'm not gonna make you learn is where all these molecules come from, okay? It used to be, a little bit more clear cut with some of these molecules, and then they found, oh, they actually come from a few different cells, and so that's why I'm not gonna make you learn these different molecules where they come from, okay? But I want you to know how you get to the end product, okay? Definitely want you to know this. So you got this molecule called angiotensinogen. It's made of the liver, but you don't need to know that. It's gonna be traveling through the blood, and it's going to come in contact with this enzyme called renin. So, this right here is your substrate, right? Or you could call it a reactant. This goes back to bio and learning enzymes. Okay. It's called your substrate or your reactant. It's a substrate because it's going to bind to that enzyme. Okay, renin is your enzyme. When that substrate, angiotensinogen, binds to this huge protein that is your enzyme, renin, renin is going to catalyze a reaction and cause angiotensinogen to be converted to a molecule called angiotensin 1. This would be your product. Now, angiotensin 1 becomes the new substrate for our next chemical reaction. So I'm going to do it like this. I'm going to call this substrate 1, enzyme 1, product 1. Okay, that's our first chemical reaction. Second chemical reaction, the product becomes the substrate for the second chemical reaction. So I'm going to call this substrate or reactant 2. It is going to get converted into another molecule in the presence of a second enzyme that I want you guys to know. This enzyme you're not going to see in the PowerPoint, but I want you to know it because there are a class of pharmaceuticals that you will absolutely come in contact with that inhibit this enzyme. And when I first made this PowerPoint a long, long time ago, those pharmaceuticals just weren't used back then, but they are now. And this enzyme here is called, what's it called? ACE. ACE, angiotensin converting enzyme. Angiotensin converting enzyme. So ACE is your second enzyme. Call it enzyme 2. So angiotensin 1 is the substrate that binds to ACE. When angiotensin 1 binds to ACE, ACE catalyzes the conversion of angiotensin 1 into angiotensin, take a guess, 2. Okay, so this we're going to call product 2. All right, now these reactions are happening in the bloodstream and as we go past certain organs. And again, we're not going to worry about kind of the details of that. Okay, now that we have angiotensin 2, it's going to do things. Angiotensin 2 kind of acts like a hormone. It's not a hormone because you can see it was not made by endocrine cells, right? It was made by this metabolic pathway as it was traveling through the bloodstream. Okay, so it's not a hormone, but it acts like a hormone in that it travels through the blood and it goes to different target sites and it does things. Okay, so it's not a hormone, but it acts a lot like a hormone. Now, I'm going to talk about 3 target sites that it goes to, 3 things that it does. On the final, I'm going to ask you to tell me 2 target sites and 2 things that it does. It does more than 3. I'm just going to talk about 3. You're going to tell me 2. Okay. All right. One thing that angiotensin will do is it will travel through the blood. So I'm going to put via the blood. And it will go to your peripheral blood vessels. And I put peripheral blood vessels up here just so you don't think that it's only working at the kidney or at your arterioles, okay? It targets blood vessels throughout your body. And what angiotensin 2 can do to your blood vessels is it will cause them to vasoconstrict. So it'll cause your blood vessels to vasoconstrict. And again, that's why I put peripheral here. We're not just talking just at the little arterioles by the glomerulus. Okay? So it'll cause vasoconstriction. And by having our blood vessels vasoconstrict, that will make our blood pressure go up. And what started this whole thing, a drop in systemic blood pressure. Okay. So we have maybe negated the stimulus, hopefully we've negated the stimulus. Now, if our blood pressure systemically goes up, does this, the fact that we caused our blood vessels to vasoconstrict and our blood pressure went up, does that cause our blood volume to go up? Does this cause our blood volume to go up? No, right? All we did, you got the same blood in your blood vessels, all we did was make your blood vessels constrict, okay? I say that because people always, underneath here, put increase in blood volume, okay? And you'll see why people do that in a minute, okay? But I put this first because I want you to see this does not increase blood volume. The next two pathways will increase blood volume, but this one does not, okay? It just increases blood pressure, that's it. Now, let's think, okay, so that negated this stimulus. But let's think it through with this here for a minute, okay? I'm gonna put in parentheses. If our systemic blood pressure goes up, okay? If blood pressure throughout our body goes up, then what should happen to our glomerular hydrostatic pressure? If blood pressure throughout the whole body goes up, then the blood pressure in the glomerulus should do what? Should go up, okay? So when our systemic blood pressure goes up, then that should cause our glomerular hydrostatic pressures to go up. And if our glomerular hydrostatic pressures go up, then that should cause our glomerular filtration rate to go back up. And now we've negated this stimulus as well. And I'm going to put here to range, back up to homeostatic range. Okay. Now, another thing that angiotensin II will do is it will go to the adrenal cortex. So again, it travels through the blood, and it will go to the adrenal cortex. And at the adrenal cortex, angiotensin II will tell the adrenal cortex to make and release aldosterone. Now, other things can cause the adrenal cortex to make and release aldosterone also. What's a hormone that you guys learned can target the adrenal cortex and cause it to make aldosterone? Starts with an A, C, D, H. Okay, good. That could cause aldosterone to be released. We could also get aldosterone released because of humoral stimuli as well. Okay, you'll see that in a minute. Okay, so aldosterone. Now we've got aldosterone in the bloodstream. Okay, and aldosterone. Where does aldosterone target? Where? Kidneys. Now you guys know more details about the kidneys. Could aldosterone target the PCT of the kidneys? What did I say last time about the PCT and the loop of Henle? That does what kind of reabsorption? Remember I said bulk reabsorption. That's your factory. It just bulk reabsorbs. And I said the latter part of the nephron is where you fine tune, right? You fine tune with hormones. So aldosterone targets the DCT of the kidneys. Okay, targets the DCT. Anytime you're going to see hormones targeting the kidneys, it will never be at the PCT. It will never be at the loop of Henle. Those two areas are bulk reabsorption. And they do some other things too, but they're just workhorses. Okay, they don't care what's in the bloodstream. Okay, they're just getting stuff done. Okay? It's the DCT and the collecting duct that starts to fine tune how much gets reabsorbed based on hormone levels. Now, aldosterone, is that a steroid hormone or a water soluble hormone? It's a steroid. So that means when it gets to the DCT, will it freely cross plasma membranes or not? It will freely cross plasma membranes. It will enter into the simple cuboidal epithelial cells of the DCT. It will bind to intracellular receptors in the simple cuboidal epithelial cells of the DCT, and it will cause genes to get turned on. In particular, it will turn on a gene that causes an increase in the number of sodium, potassium, ATPase pumps. That's the gene it targets. It causes the gene for sodium, potassium, ATPase pumps to crank crank up production of those pumps. Remember, this is a counter transport pump. It moves sodium one direction, potassium the opposite direction. So by having more of these pumps in the simple cuboidal epithelial cells, in their plasma membranes, what this does is, it causes an increase in the reabsorption of what? Sodium. Increase in sodium reabsorption at the DCT. It's a counter transport pump, so that means as we're reabsorbing more sodium, we have to be doing more what with potassium? Secretion does the opposite. It's a counter transport pump. So we're reabsorbing more sodium, we're secreting more potassium, and water will passively follow the sodium. So as we're reabsorbing more sodium, water passively follows, and we increase water reabsorption. As we increase water reabsorption, what does that do to our blood volume? Increases blood volume. As we increase blood volume, what happens to our blood pressure? Increases. So here, we increase blood pressure by increasing blood volume. The first pathway, we didn't do anything with blood volume. We only increased blood pressure. This pathway increases blood volume to get the blood pressure to go up. And again, we've just negated our stimulus. And again, we can think it through affecting GFR. So if our systemic blood pressure goes up, just like we did before, if blood pressure throughout the whole body goes up, then that should mean that the blood pressure in the glomerulus goes up. And if blood pressure in the glomerulus goes up, then our GFR should go back up to range also. Now, so that we don't have to talk about aldosterone again in these lectures, let's just add in a few more things just to think the story through, okay? So again, that we don't have to redo the whole thing again when we encounter it on another slide. So on your test, I could ask you things very straightforward just like this, right? If you've got aldosterone in the bloodstream, what will that do to reabsorption of sodium at the DCT? And you would say, oh, it goes up, okay? But I could also ask you things slightly differently, right? I could say, if you've got aldosterone in the bloodstream, and if that causes more sodium to get reabsorbed, then the end result of this is gonna be that your blood sodium levels are gonna do what? If you're reabsorbing more sodium, your blood sodium levels will go up, okay? So I could ask it to you that way. And if your blood sodium levels are going up because you're reabsorbing more sodium and you're secreting more potassium, then that means that your blood potassium levels would be going down. Okay, good. And if your blood sodium levels are going up, then that means in your urine, your sodium levels would be going what? Down. And if your blood potassium levels are going down, then that means your urine potassium levels are going up, okay? And I could ask you any of those ways, okay? So for me, if anybody ever asked me a question about aldosterone, I just start writing this stuff down. So I've got all what it does off to the side, and then I look at my choices, and I choose from what I have already written down. And that way I don't confuse myself, okay? Let's follow up over here. If we're reabsorbing more water and our blood volume goes up, then that means our urine output goes what? Down. Urine output, urine volume, same thing. Okay. All right, so one more place. Angiotensin 2. will also go to the hypothalamus. And I'm gonna lump these together and posterior pituitary. If you see aldosterone in the bloodstream, and almost always you have some level of aldosterone in your bloodstream, that's almost a given, okay? If you see aldosterone in your bloodstream, which you basically always do, you will also see another hormone because they tend to always work together. Aldosterone can affect water content through sodium levels. Okay? But this other hormone doesn't deal with individual ions, it's dealing with water. And what's this other hormone that's made in the hypothalamus and released from the posterior pituitary?
ADH.
Which one?
ADH.
ADH. Okay, so ADH, also called vasopressin. So ADH travels through the bloodstream. It's going to go to the kidneys, and it primarily targets the collecting ducts of the kidneys. Now, I think about the DCT and the collecting duct kind of together because what happens at one will also influence the other area. So although aldosterone works primarily to DCT, it can affect the collecting duct as well, and vice versa. Okay, so I tend to think of these two areas together, and I don't care if you do that either, it's fine. So, ADH, is that a steroid hormone or a water-soluble hormone? It's water-soluble. So what ADH does, ADH causes an increase in the number of aquaporins. That's what ADH does. It causes more water channels to get inserted into the simple columnar epithelial cells here in the collecting duct. It causes more water channels to get inserted. Okay, aquaporins, water channels. There are no water pumps, but there are water channels, aquaporins. And by having more water channels or aquaporins at the collecting duct, that then allows more water to get reabsorbed. So we see an increase in water reabsorption. As we increase water reabsorption, our blood volume goes where? Up. As our blood volume goes up, our urine output goes down. And as our blood volume goes up, then our blood pressure goes up. And again, that's back to range, back to homeostatic range. And again, the same basic idea. As your systemic blood pressure goes up, then that will cause the blood pressure in your glomerulus to go up. And as the blood pressure in your glomerulus goes up, that causes your filtration rate to go up. And again, you're back to range and negated that original stimulus up there. So that is your renin-angiotensin system. Okay. So I will ask you, give me a stimulus that triggers this system. I will ask you where the enzyme renin comes from. You'll say juxtaglomerular complex or juxtaglomerular apparatus. I'll ask you the chemical reactions that renin is involved in or that it catalyzes, something like that. I'm going to ask you for substrate, enzyme product, substrate, enzyme product, okay? Angiotensinogen in the presence of renin gets converted to angiotensin 1. Angiotensin 1 in the presence of ACE gets converted into angiotensin 2. Angiotensin 2 acts like a hormone. It travels through the bloodstream and it targets multiple things. We've listed 3 things. You will tell me 2 target sites and what happens at those target sites. and then I'll ask you what the final goal is. The final goal is to get systemic blood pressure back up. Negate that stimulus.
What's the C in H? Like,
Converting.
okay.
Angiotensin converting enzyme. And actually that brings me back to, I said that this enzyme here was a target of a very popular pharmaceutical now. There are a group of drugs that are called ACE inhibitors. ACE inhibitors. So if you have a patient that is on ACE inhibitors, it's because their blood pressure at a baseline level is too what?
No.
If they're given ACE inhibitors, it's because their baseline blood pressure is too what?
Low.
So let's think it through. If their blood pressure is too low and we give them an ACE inhibitor, everything stops right here, right? If we inhibit this, everything stops. And if all this stops,
It doesn't bring it up.
then we can't get blood pressure to go up.
So it's too high.
So people that have high
Blood
blood pressure take ACE inhibitors to, it won't stop this pathway, but it slows it down, okay? People that have high blood pressure, you wanna slow this pathway down so that they're not reabsorbing as much water, so that they're not reabsorbing as much sodium, so that they're not retaining so much water. People that have high blood pressure, you want them to urinate, right? You don't want them holding on to the water, okay? So you wanna slow this pathway down. Okay, we're gonna talk about some more hormones. Questions on that stuff?
One question.
Yeah.
What did you say the AT paste does? Like the pumps AT paste?
Yeah, the sodium potassium ATPase pumps. So those are active transport pumps. That's why it's an ATPase. It hydrolyzes ATP and uses the energy. Those pumps move sodium one direction and potassium the other direction. So usually, when you're looking at just any old cell, so usually what this pump will do is it'll take 3 sodiums that came into the cell. Here, let's back up for a second, because this pump is important to know. So at rest, you've got more sodium on the outside of your cells, and you've got more potassium on the inside of your cells. That's at rest. And also at rest, you've got channels that are called leak sodium channels. And at rest, you've got these leak potassium channels that are just always open, which means at rest, sodium can diffuse into the cell, and at rest, potassium can diffuse out of the cell. And if that's all that you had at rest, these 2 ions would reach equilibrium pretty quick, right? You'd have sodium diffusing in till you had equal amounts on either side. You'd have potassium diffusing out until you had equal amounts on either side. And if those ions reach equilibrium, you will die, right? So every cell in your body cannot let that happen, okay? You will die if that happens. And you would die if that happens because if you've got equal amounts of sodium in and out of your cells, you could never generate an action potential, right? To generate an action potential, you must have sodium rush into the cell, and it would never do that if you had equilibrium. So if this equilibrium happens, you will die because you can't make your heart contract, you can't make your skeletal muscles contract, you wouldn't be able to breathe, you would die if that happens. So at rest, this is all at rest. At rest, about 40% of all the ATP that you make, a cell makes, 40% of all ATP a cell makes at rest powers that pump. Powers that sodium potassium ATP ACE pump. And what that pump then does is that pump, before you can reach equilibrium, before that happens, this pump is gonna take 3 sodiums that came in and put them back on the outside, back on the outside. And then that pump is gonna take 2 potassiums that left the cell and pump them back on the inside. And this pump is always working, and it uses ATP, 1 ATP to power 3 sodiums that came in and put it back out, 2 potassiums that left and put it back in. And because of that pump, primarily, and some other things, because of that, that's why we don't have this. Instead, we have high sodium on the outside, and we've got high potassium on the inside, because that pump is always working. And it just so happens that it's a real popular pump, and it's used here too. Yep. Okay, anything else before we talk about some more hormones? Okay, let's talk about some more hormones, and then we'll move into the tubing. So we want to talk about these 2 hormones, and we're still talking about glomerular filtration rate, okay? We're still kind of working around that. We want to talk about these 2 hormones called AMP and BMP, okay? So, let me come back here for a second. So I said that you almost always have aldosterone and ADH in your bloodstream. Some level, you've got aldosterone and ADH in your bloodstream. And these guys work together. These are agonists. They work together to not regulate sodium levels, but to regulate water levels, blood volume and blood pressure. The way they do it is different, the mechanism's different, but they both help to increase blood volume and increase blood pressure. And they're almost always in the bloodstream, and these guys are important to keep from getting dehydrated. I said that there are many mechanisms to keep you from getting dehydrated. This is one of many, okay? Has anybody started their case study? It's a stupid question, right? If you haven't, I'm assuming you haven't, you will become very familiar with one or both of these hormones, okay? That's my generous hint to you. There you go. Okay. So, these hormones here, AMP and BMP, they hardly ever are in your bloodstream, but they also work together, okay? So they're agonists, they are gonna work together. They are antagonists to ADH and aldosterone. ADH and aldosterone are usually in your bloodstream. These guys are hardly ever in your bloodstream. And the reason they're hardly ever in your bloodstream is because they're only going to be released if you have excessively high blood volume and blood pressure. And I will use that kind of wording on your test, okay? So if your blood pressure and blood volume go up a little bit, these hormones are not going to be released, okay? You must have excessively high blood volume and blood pressure to get these guys released. All right, now, let's think about what they do if you do have excessively high blood volume and blood pressure. If your blood volume and blood pressure is severely or excessively, okay, and again, you'll see me use those kinds of words. If I just say blood volume and blood pressure goes up, no, not these hormones. So I've got to make it seem extreme in some way, shape, or form. Severe, excessive, extremely high. Then what happens is, if your blood volume and your blood pressure are really high, excessively high, as blood comes back into the heart, it's going to stretch more than normal, okay? Now remember, when blood comes back to your heart, your atria and ventricles stretch. That's just what happens. If your blood volume and blood pressure are really high, then it's going to cause your atria to stretch even more, okay? And when the atria and your ventricles stretch to a excessive amount, let's just say that, that's when these hormones are released. So ANP, atrial natriuretic peptide, let me go back a slide so you can see the words. ANP, atrial natriuretic peptide. Sometimes you see the P replaced with an H, peptide or hormone. It comes from endocrine cells in the atria of your heart. It's released when the atria stretch excessively. The atria are only going to stretch excessively if you have excessively high blood volume and blood pressure. Otherwise, your atria stretch a little bit, and that hormone will not be released. BNP stands for brain natriuretic peptide, and again, sometimes you'll see the P replaced with an H. It does not come from your brain, okay? It was maintained correctly. It comes from the ventricles of your heart. And again, it comes from the ventricles of your heart if your ventricles stretch excessively, like they would if you have excessively high blood volume and blood pressure. Your ventricles will stretch, but if they excessively stretch, that's when this hormone's released. Now, these guys, they are antagonistic to these hormones. If these hormones are trying to get you to retain water, so your blood volume and blood pressure go up, those hormones are going to do just the opposite. They're going to try to make you dump water, a lot of water, so your blood volume and blood pressure come down. Now, how do they do that? Okay, they do that kind of two major ways. First of all, they will cause dilation of the afferent arterioles. Okay, so I want you to visualize that. As blood comes into the glomerulus, it causes the afferent arterioles to dilate. So that makes it easier for blood to come into the glomerulus. It causes constriction of the efferent arterioles. Okay, so again, visualize. It makes it easier for blood to come into the glomerulus, harder for it to leave. Can I erase this? Do you guys have this? Okay. Okay, so AMP and BMP are going to cause dilation of the afferent arteriole and constriction of the efferent arteriole. The end result of that, so blood comes into the glomerulus easier, harder to leave. What does that do to the pressure in the glomerulus? Make it go up or down?
Increase.
Comes in real easy, now it's hard to get out. Pops it up, okay? So that's gonna pop up your glomerular hydrostatic pressure. And pops it up. And as your glomerular hydrostatic pressure goes up, that causes your glomerular filtration rate to go up. Now, I want you to stop and think for a second though, okay? I want you to get right, really think for a minute. Before those hormones were released, okay? Before those hormones were released and caused that, we said they were released because blood volume and blood pressure were really high. Before those hormones get released, if blood volume and blood pressure are really high, what is your glomerular hydrostatic pressure going to be if your blood volume and blood pressure are really high? It's going to be high, right? Stick with me. Let me say it again. Before these are released, if your blood volume and blood pressure are really high, right, then that means that the pressure in your glomerulus is going to be really high, which means your glomerular filtration rate is going to be pretty high. Now, usually we're all about bringing things back into homeostasis, right? And we are in this case, but we're playing the long game in this case, okay? So what these hormones do is they make it go even higher. They make your glomerular hydrostatic pressure and your glomerular filtration rate go even higher. Now, why would we do this? We make all this really go high because if our filtration rate is really high, what does that mean to our urine output? Actually, let me back up, okay? Let me back up. Let me add one more thing that will help this story. Not only do these hormones do this, okay, what we just said, but at the same time, they inhibit water reabsorption a couple ways. One thing that they can do is inhibit aldosterone's release and inhibit ADH's release. So these hormones, AMP and BMP, they make glomerular hydrostatic pressure and filtration rate go even higher than they were already, while they inhibit aldosterone and ADH so that we can't reabsorb as much water. And if we can't reabsorb as much water down at the DCT and the collecting duct, by having more filtrate running through there that we can't reabsorb, what's that gonna do to our urine output? It's gonna increase it. So this pathway is all about ramping up urine output. And as we start dumping a bunch of urine, what's that do to our blood volume?
Decrease.
It will decrease. And as our blood pressure comes back down, as our blood volume comes back down, our blood pressure comes back down to range. So these hormones, again, they're not released just because blood pressure goes up a little bit. These hormones are released when you have excessively high blood volume and blood pressure because they're pretty dramatic. They're going to short-term ramp everything up at the glomerulus and shut all this stuff that normally happens at the DCT and the collecting ducts down because these hormones are normally in our bloodstream. So it shuts this stuff down. It ramps up even more what happens at the glomerulus, also that we can have more urine output. And by increasing that urine output, we ultimately get our blood volume down. It just is gonna take a moment to do that. It doesn't take too long, but it's more of a long game. Okay, questions on AMP and BMP? All right, so now let's say a couple things about that autonomic nervous system thing. So I said at the, where am I? At the glomerulus, okay? I said that the autonomic nervous system can regulate GFR, but it won't homeostatically try to bring it back into range, okay? So the autonomic nervous system I can't remember the words I used. The autonomic nervous system can help to regulate GFR. It just won't homeostatically try to bring it back into range, like we typically see the autonomic nervous system do. And what the autonomic nervous system is gonna do here is, again, if you are in this fight or flight mode, okay? If you're in this fight or flight response and you go into sympathetic mode, then what you ultimately want to do is you want to spend your resources fighting or fleeing from a situation, which means that you want to send a lot of blood out to your skeletal muscles so that you can get oxygen and nutrients like glucose out to your skeletal muscles so they can make ATP, and you want to take away their waste products from skeletal muscles. What you don't want to be doing is sending a lot of blood over to the kidneys to get filtered right now. You want to bypass the kidneys a bit for a short period of time so you can send all this blood over to the muscles so they can fight or flee for you. And the way that you do that is the sympathetic division of the autonomic nervous system will come in and cause vasoconstriction of the afferent arterioles. And it can be so strong that it basically shuts down the afferent arteriole so you can't get any blood into the glomerulus. Okay? And if you're not getting any blood into the glomerulus because you vasoconstricted your afferent arteriole so much, that obviously is going to slow your GFR down. And it could make your GFR go to 0. Again, for short periods of time, it's okay to do this. You just don't want it happening for long periods of time. So, we'll leave it at that. Okay, so it can regulate, it's just not about trying to bring it into homeostasis. It's about coming in and shutting everything down. It comes in and it overrides anything that's happening through autoregulation. The autonomic nervous system, the sympathetic division can completely override that so that the arterioles can't adjust through autoregulation. They're basically shut down so that we can get that blood shunted somewhere else to your skeletal muscles so that they get the maximum oxygen, nutrients, and waste is taken away. Okay, all right, we're leaving the corpuscle. Okay, we've got our filtrate now. So now we go into the PCT. We go into the PCT. We go into the PCT, and remember the PCT and the leukotenylene are bulk reabsorption, right? Other things happen there as well, but we're gonna just reabsorb as much as we can because we have to reabsorb 99% of everything we just formed. So at the PCT, we're going to reabsorb 60 to 70% of that 99%. So again, this is the primary job of the PCT, reabsorption. Now, what kinds of things get reabsorbed here? Okay, so we've already mentioned this, but I just want to reiterate what I would want you to know for the test. Okay? At the PCT, the primary job, not the only job, the primary job is reabsorption. To help facilitate that reabsorption, remember we said these cells, these simple cuboidal epithelial cells have microvilli on their apical surface. That was on the previous lecture. What kinds of things get reabsorbed here? Organic nutrients, so glucose, amino acids. That also tells you that we have glucose pumps and pumps for amino acids here as well. So if I were to ask you some multiple choice question, and I said something about, you know, were there glucose pumps? You would say, yes, there's glucose pumps. Here, that's how we reabsorb these organic nutrients. We're gonna do some active reabsorption of ions. Active reabsorption just means we're gonna use active transport pumps to do it. You do not need to know which ions here at the PCT. We'll worry about individual ions later. Okay, so you don't need to know these individual ions. I just would like you to know that you do use active transport pumps at the PCT as well for reabsorption. We're gonna reabsorb water here because water is gonna passively follow all these solutes. Okay? So as we're reabsorbing glucose, amino acids, all these ions, water will follow all that. So we reabsorb water. And we do, you can barely see it down here, but we do some active secretion at the PCT. It's just really minimal compared to all the reabsorption that takes place. You don't need to worry about urea and chloride. This is just saying anything that gets reabsorbed that's lipid soluble will just passively diffuse. Okay? That's all this is saying. Anything that's lipid soluble will just be passively diffusing and get reabsorbed here. That's all that's saying. Okay. This slide right here, the whole point of this slide is I just want you to visualize what you have to cross for something to get reabsorbed or secreted for that matter. And we've already done this on the board, but I just want to go over it one more time so you see it on this slide. Okay? So let's say we're here at the PCT. Here's a cross section of the PCT. We've got simple cuboidal epithelia on the apical surface. We've got microvilli. In here would be your tubular fluid or your filtrate, and then out here would be your peritubular fluid. Okay. You would have capillaries going around this. The capillaries would be out here. If we look at this on here, so this is where the tubular fluid is in here. Here's your microvilli. Here's your simple cuboidal epithelial cell. Right here is your peritubular fluid, this, and then here's your peritubular capillary. So if we're going to reabsorb, then that means, let's say we're gonna reabsorb an ion, let's say. Then that ion has to move across this apical plasma membrane, either through a channel or with pumps. Okay? If it's lipid soluble, it can just freely diffuse, but anything that's water soluble needs a pump or a channel right here. Remember, there are no water pumps. And then it has to diffuse through the cell and then cross this basal plasma membrane here. So again, if it's an ion, it has to cross this membrane with a pump or channel. Doesn't have to be the same one it used here, but pump or channel. Then it will be in the peritubular fluid or the interstitial fluid, and then it can diffuse into the blood, into the peritubular capillaries. So, at the very least, you have to cross one plasma membrane, two plasma membranes, and then depending on how it's getting into the bloodstream, it either will go in between cells or it will cross plasma membranes of the simple squamous epithelial cells here as well. So at the very least, 1, 2, at the most, 1, 2, I'm showing over there, but like 3, 4. Okay? Usually for the capillaries, they can kind of come in between the cells like that. All right. Right, we're going to the loop of Henle. Questions before I start in on counter-current multiplication. All right, let's do it. Okay, so we've got our PCT here. Here's our loop of Henle. Now, when you look at the loop of Henle, the way I drew it is not accurate. And let's look at how it really looks, and I'll tell you why I didn't draw it that way. So, I'll come back to this slide in a minute. So, here's our loop of Henle. And when you look at the loop of Henle, you've got a descending limb and an ascending limb. And when you look at those limbs, each limb has what's called a thin segment and a thick segment. And I didn't draw that part, but let's look and see what it looks like. Here's the descending limb right here, and you can see that most of the descending limb is skinny right there. It's got a thick part right here, and then most of it's this thin part right there. When you look at the ascending limb, it's got this thin part and then this thick part. Okay? So for the descending limb, most of it's thin, and for the ascending limb, most of it's thick. And I just didn't separate those two things out. I didn't give each limb a thin and a thick side, a thin and a thick. I just didn't worry about it. Okay. So for the descending limb, most of it's thin, back here. And for the ascending limb, this part, most of it's thick. All right, now, before we talk about how this whole thing works, let's come back and just say what we're gonna see here, then we'll talk about the benefits of this setup, and then we'll talk about the details of the mechanism, how it actually works. So what we're gonna do here at the nephron loop or the loop of Henle is this thing called countercurrent multiplication. What countercurrent multiplication is going to do is it's going to allow us to reabsorb about half of the water and about 2/3 of the sodium and chloride that are still in that filtrate. Now remember, the PCT and the loop of Henle, we just want to reabsorb as much as we can. We want to bulk reabsorb. And this setup allows us to do a lot of bulk reabsorption for sodium chloride and water. It's just a really good way of reabsorbing a lot, about half of the water and about 2/3 of the sodium and chloride that's still in that filtrate. So that by the time we get over here to the DCT, we can start fine tuning things. Okay. Now, let's talk about the benefits, and then we'll come back and talk about how this works. Okay, so I'm gonna come back to this. And I'm gonna come over here. The benefit of this mechanism, this counter-current multiplication, is this system is always working as long as you have filtrate moving down the descending limb at the same time that you have filtrate moving up the ascending limb. As long as that's happening, this mechanism works. You don't need another system coming in to say, hey, time to start. You don't need another system coming in to say, hey, time to stop. Like, for example, you do with hormones. Hormones are only going to be released if you have a stimulus that says, hey, increase your production. This mechanism always works. You don't have to have anything monitoring it. It will just work. And it works like a factory, okay? You don't need any oversight to this thing. It's just gonna be cranking out reabsorption of water, sodium, and chloride. Now, this system only works if you've got filtrate moving in opposite directions at the same time with limbs that are close together. If these limbs were far apart, this mechanism would not work. And to fully understand it, we gotta put the collecting duct in here as well. Okay, so that's one benefit of this system. You don't need any oversight, it's always working, and it's always working like in top production, right? So it's a very effective, a very efficient way to reabsorb a lot of sodium, a lot of chloride, and a lot of water. The other benefit of this system is, remember when we looked out here in this peritubular fluid out here? I said that when you were close to the cortex, it was about 300 milliosmoles out here. And as you got deeper in the medulla, the osmolarity increased. So there was about 1,200 milliosmoles down here. Now, you have to have different mechanisms keeping this extracellular fluid solute rich. It doesn't just stay like that, right? These solutes will be diffusing, getting secreted, reabsorbed, going into capillaries. They're not just gonna be sitting here. So you have to have something that keeps this very solute rich. And we said that there's almost always ADH in the bloodstream. And if there's almost always ADH in the bloodstream, so I'm gonna put with ADH, then that means almost always we should have a lot of water channels in the collecting duct, because that's what ADH does. So let's put a bunch of water channels in here. Now, that's all well and good, but water is not going to leave the collecting duct and come out here, even with all these water channels, unless we got a lot of solutes out here. It just won't do it. So this mechanism, countercurrent multiplication, is one of many ways of helping to keep a lot of solutes out here in the extracellular fluid, so that in the collecting duct, we can reabsorb water under the influence of ADH. Okay, let me say it again. Countercurrent multiplication is one of many mechanisms, it's a particularly good one, that helps to keep the solute concentration around the collecting duct high, so that water can get reabsorbed from the collecting duct under the influence of ADH, which is almost always in the bloodstream. So this system is a very nice system. Okay? Now, how's it work? All right, so it works because, again, we have fluid moving in opposite directions. That's the counter-current part of it. We got filtrate moving down the descending limb, at the same time we have filtrate moving up the ascending limb, counter-current. The second thing is, those limbs are close together. We said we gotta have that, the limbs have to be close together, which they are. Third, the limbs have different permeabilities. When we look at the thin descending limb, remember I said the descending limb was mostly thin, that's why I didn't bother drawing it. When we look at this descending limb, it is permeable to water. This part's permeable to water, but relatively impermeable to other solutes. So what that basically means is, when you look at the thin descending limb, there are water channels in here, but there aren't channels for other solutes. You're not gonna see sodium channels in there. You're not gonna see chloride channels in there. You're not gonna see pumps for ions over here. The descending limb is impermeable to most solutes. You can't say it's impermeable to all solutes, because if it's lipid soluble, it can freely cross any membrane. You can never stop something that's lipid soluble. But anything that's water soluble, it can't cross the descending limb, except water. There are water channels there. It's permeable to water and not to any other water soluble solutes, like sodium, like chloride. Okay, so I'm gonna put some water channels here. Now, if we look at the ascending limb, it is the opposite. The ascending limb, in particular the thick ascending limb, and most of it is the thick part, this is relatively impermeable to water, meaning there are no water channels over here. Again, we can never completely stop water because water can freely cross a membrane. But if we don't have water channels, it makes it a whole lot harder to leave. That's why it says relatively impermeable to water. There are no water channels over here, but there are active transport pumps for sodium and chloride over here. So there's sodium, chloride pumps. Sodium, chloride pumps. Okay. All right, so now let's go through this and see how it works, okay? This thing is called counter current multiplication. We already know what the counter current means. It means filtrates moving in opposite directions in these two limbs at the same time. Filtrate moves down the descending at the same time it's moving up the ascending. Now, what's the multiplicative part? Counter current multiplication. It works like this. Let's start on the ascending limb. Sodium and chloride are being actively transported out. Okay, so sodium and chloride are being actively transported out. Now, as we have filtrate coming down the descending limb, as that filtrate comes down the descending limb, having all these solutes out in the peritubular fluid, that's going to drive the water to come out even faster. It's going to make osmosis occur faster because we have a greater concentration difference because all these solutes are out here. Then this filtrate, as it comes down here and starts to head up into the ascending limb, this filtrate here, because all that water came out of it, this filtrate now has a high osmolarity. Let's stop and think about that for a minute. High osmolarity just means there's a lot of stuff in it and little water. There's little water because so much water came out as it came down the descending limb. And now as that filtrate starts heading up the ascending limb, it has little water, but still a lot of solutes in it. It's got a high osmolarity. Because it's so concentrated, that filtrate, it's not diluted out with a lot of water, because it's so concentrated, the sodium and chloride bind to those pumps really fast, because it's nice and concentrated. Because that filtrate's so concentrated, the sodium and chloride bind to those pumps quickly, and boom, we pump the sodium and chloride out really fast. Having all that sodium and chloride out here in the interstitial fluid, now as we have more filtrate coming down, out comes the water. Having all that water comes out makes this filtrate nice and concentrated. That concentrated filtrate allows those pumps to pump really fast. Sodium and chloride get pumped out really fast. Now out here in the interstitial fluid is very concentrated with solutes. New filtrate comes down, out comes that water really fast. That's the multiplicative part. What happens in one limb drives what happens in the other limb. The fact that the sodium and chloride are being pumped out into this interstitial fluid is driving the water out faster here. If we didn't have solutes out here, the water wouldn't come out, or it would come out really slowly. Yeah. No. Having all that water coming out so fast makes this filtrate really concentrated. A concentrated filtrate means the sodium and chloride combine real quick to those pumps, thus we pump the sodium and chloride out really fast. As the sodium and chloride get pumped out really fast, the new filtrate coming down, out comes the water really fast. So what happens in one limb drives what happens in the other limb, what happens in one limb drives what happens in the other. It's a multiplicative event. If we didn't have all this water coming out, this filtrate would be very dilute. It wouldn't be very concentrated. It would take longer for the sodium and chloride to bind. We wouldn't pump as much out. If we didn't have as much sodium and chloride out here, as much water wouldn't come out. We wouldn't have this bulk warehouse kind of event happening where it's just one limb drives the other, drives the other, drives the other. It's just constantly happening. And you end up getting a whole lot of sodium, a whole lot of chloride, and a whole lot of water getting reabsorbed. Okay, countercurrent modification. Questions? It is 8:15. I know you're gonna kill me when I say this. I need about 30 more minutes to finish up. So, we can take a little break right now. And this is because we didn't have lecture last week. Remember, I gave you the week off so that we would get it done this week. We don't need to do lab, right? Lab's done, right? You already did lab, you got your videos. Is there a reason to do lab tonight? We can go up to lab, it's fine. So but I need 30 more minutes to make any headway, and we still won't finish it, which is fine, but it'll give us just the right amount to finish next week. So I'm gonna do a 7-minute break right now, okay? Let's just call it a 10-minute break. I'll try to get things done in 20 minutes. If we look at that filtrate that we started with, so the filtrate that we started with is the PCT. Remember, look pretty much like blood plasma, except it should not have any plasma proteins in it. But otherwise, at the PCT, at least when it starts in the PCT, it really looks like blood plasma, because anything that's small enough came out. By the time that we come into the DCT, it looks a lot different now, because we've reabsorbed a lot of stuff at this point. So now our filtrate's starting to get more condensed, so that by the time that that filtrate leaves the collecting duct, remember, we need it to be about 4 times more concentrated than blood plasma, which will mean that we've reabsorbed most of that water back into the bloodstream. So this is the DCT and the collecting duct. This is where we make our kind of last final alterations. Some of that, a lot of that will be under the influence of hormones. Hormones detecting humoral stimuli, how much sodium's in the blood, how much potassium's in the blood, how much calcium's in the blood, how much glucose is in the blood, what the blood osmolarity is, how concentrated is the blood. All of those kinds of stimuli, humoral stimuli, can cause hormones to be released that tell the DCT and the collecting duct, reabsorb a little bit more of this, secrete a little bit more of that. Not everything that happens at the DCT and the collecting duct is under the influence of hormones, but a lot of it is. Okay, we'll look at pH, which is not under the influence of hormones. But everything else that we'll talk about is under the influence of hormones. And you already know these hormones, so it'll just be a quick review of some of these hormones. So the hormones that I want you to know that work at the DCT and or collecting duct. I'm just gonna make a list, that way you're very clear in what I want you to know. Because some of these slides have a little bit more information in them and stuff like that, so let's just make a list. So we'll say at the DCT and collecting them. We've got aldosterone. So you already know what aldosterone does, okay? So just, again, a quick review. It's gonna increase sodium reabsorption. It's gonna increase potassium secretion. Water's gonna follow that sodium, so we'll increase water reabsorption. That'll increase our blood volume. And that increases our blood pressure. Okay? And again, make sure that you think about it different ways as well. As we increase sodium reabsorption, that's going to increase our blood sodium levels. As we increase potassium secretion, that's going to decrease our blood potassium levels. And whatever we do in the blood, we're doing the opposite to the urine. Okay, whatever we do to the blood, the opposite is happening to the urine. As we increase water reabsorption and increase blood volume, we're decreasing urine output. Okay. And now that we know what aldosterone does, we can then think about what would cause it to be released humorally. Okay? So, stimuli. Stimuli that will cause release of aldosterone. We have learned ACTH can cause the release of aldosterone. We learned today that angiotensin II can cause the release of aldosterone. And now that we know what it does with blood levels, we now know that it can be released because of humoral stimuli also. So if its job is to increase blood sodium levels, then what can cause it to be released would be a drop in blood sodium levels. If its job is to decrease blood potassium levels, then what can cause it to be released would be increase in blood potassium levels. And if it increases water reabsorption, it increases blood volume and blood pressure, then a drop in blood pressure can cause it to be released as well. Okay, then, let's see. So let's make a comment here about this. There are two places on the next couple slides that talk about excessive aldosterone release, okay? And I want you to first be aware that this is not normal, okay? If we have excessive aldosterone release, there's a big problem going on somewhere. Maybe, for example, you have a tumor on the adrenal cortex. That could cause excessive amounts of aldosterone to be released. But let's say we did. Let's say there was something major going on, like a tumor on the adrenal gland. And let's say we did have excessive aldosterone release. That can get dangerous really quickly because if we have too much aldosterone, and remember, we almost always have some in the bloodstream, but if we have an excessive amount, then we're going to end up secreting way too much potassium. So if we have excessive aldosterone, we're going to get rid of way too much potassium. And our blood potassium levels, instead of just coming down where they should be, are going to go way too low. And when you have really low potassium, that's called hypokalemia. Hypokalemia is where you have really low potassium levels. That can get life-threateningly dangerous. Because if your plasma potassium levels get too low, your heart will not work properly. Again, it has to do with action potentials. You need the right amount of sodium and potassium for action potentials, and calcium really for that matter. Okay, I'll come back and say something else about excessive aldosterone release when we talk about pH. Okay, we'll come back to that. PTH. PTH, we learned, comes from the parathyroid glands, and PTH's job is to increase calcium reabsorption. as we increase calcium reabsorption, that causes our blood calcium levels to come up. And as our blood calcium levels come up, that means our urine calcium levels are dropping. So knowing that that's the job of PTH, then we know that the stimulus that would cause it to be released would be when blood calcium levels are too low. This slide right here is just talking about some things that get secreted in the DCT, okay? So there are a variety of different things that can get secreted in the DCT. We already saw that potassium can get secreted under the influence of aldosterone. Let's talk about calcium. So we've seen here that PTH can cause calcium to get reabsorbed, but we also know that calcitonin also works at the kidneys, and it would work at the DCT, and calcitonin's job is to increase calcium secretion. And as we increase calcium secretion, that's going to cause our blood calcium levels to drop. And if our blood calcium levels are going down, that means our urine calcium levels are going up. And what would cause calcitonin to be released would be exactly the opposite of what causes PTH to be released. So stimuli causing release of calcitonin would be when our blood calcium levels are too high. So potassium can be secreted at the DCT under the influence of aldosterone. Calcium can get secreted at the DCT under the influence of calcitonin. We're going to talk about hydrogen ions in just a minute. A variety of other organic acids, bases, drug metabolites. PCN stands for penicillin. Various pharmaceuticals that you might take, either they or their metabolites often get secreted at the DCT. If they didn't get filtered out at the corpuscle and they're still in the blood, then this is where they tend to get removed. And part of the research and development of making a new pharmaceutical is to make sure that if you're being introduced a drug into your system, a pharmaceutical, there has to be some way of getting rid of it, right? It's either going to get broken down by the liver or it's going to be secreted by the kidneys. And that's just part of the research and development, is to make sure that you already have some mechanism that that pharmaceutical can work off of to be eliminated from your body. So any pharmaceutical is already working on your own endogenous pumps or channels or pathways or receptors or enzymes or whatever. And that's part of that mechanism. Good study. All right, then I'm going to come back to this. This is looking at pH and hydrogen ions. I'm going to come back to that in just a minute. This right here is just doing some more hormones. So we've already done aldosterone. I'm going to add ADH to the mix. And then this down here is talking about some things that we didn't really go into. So you can kind of ignore this part right here. So I'm going to add ADH over here. So again, ADH and aldosterone, almost always in the bloodstream at some level. Aldosterone's job is to influence minerals and water will follow. ADH's job is to cause more water to get reabsorbed. As we increase water reabsorption, we increase our blood volume. As our blood volume goes up, our blood pressure goes up. And as our blood volume goes up, our urine output goes down. right, so then, what we're gonna do is we're gonna talk about this slide, and then we're gonna talk about this slide, and then that leaves just the urination reflex, and then we're done, okay? So we're gonna talk about pH and the bloodstream, okay, pH and the bloodstream. Can I erase that? Quick review on pH. And we're gonna talk more about pH next week. pH is gonna be a big part of your final, okay? pH is a big deal. So when you think about pH, first of all, blood pH, I want you to know this. Most of you missed this on your last test, so I will ask you this again, okay? The normal blood pH, 7.35, 7.45. That's your normal range right there, okay? A lot of you got close, but you weren't quite there, okay? Close, not quite. All right, so when you look at pH, it's on a scale from 0 to 14, 7 being right in the middle. If you take water, okay, just pure water, okay, put that water in a beaker, you are obviously gonna see water molecules in there, H2Os floating around in there. What you're also gonna see in that beaker of water at a pH of 7 is you're gonna see equal numbers of hydrogens to hydroxide ions. Hydrogen ions to hydroxide ions. If you put these two together, what do you got? What do you got? H2O, water. So when you look in that beaker of water, you are gonna see equal number of just hydrogens floating around to equal number of hydroxides floating around to just H2Os in there, okay? You've got all of that at a neutral pH, okay? Pure water is a neutral pH, pH of 7. If I started dumping hydrogen ions into that beaker of water, then I would have more free hydrogen ions and my pH would drop, okay? So the lower my pH is, the more free hydrogen ions that are floating around in there. If I started taking away hydrogen ions from that beaker and I had less free hydrogens floating around, my pH would be higher, okay? So a low pH means I have more free hydrogens just floating around in there. A higher pH means I have less free hydrogens floating around in there. And a neutral pH means I have equal numbers of hydrogens to hydroxides, pure water, okay? Now, as I go down on the pH scale, is that more acidic or more basic? More acidic. More acidic means more hydrogen ions, a lower pH number. Okay? As I go up on the scale, that's more basic or alkaline. I have less hydrogens and my pH number is higher. Remember, every unit is equal to a 10-fold change in hydrogen ion concentration. Okay? As I go from a pH, not in your blood, you would die if this happened, but let's just say a beaker of solution, as I went from a pH of 7 to 4. More or less acidic, more acidic, more or less free hydrogen ions, more free hydrogens. Now, how many times more? So 7 to 6 is how many times? 10 times more. 6 to 5 is 10 times more. I'm gonna write this out. 7 to 6 is 10 times more. 6 to 5, 10 times. 5 to 4, 10 times. There we go. 10 times 10 times 10, 1,000 times more hydrogen ions. Or you could say 10 to the third times more, okay? It's not 30, okay? Not 30. 10 times 10 times 10. All right. Now, homeostatically regulating pH. There are two systems that do that. The kidneys, and what's the other one that you guys learned about? The lungs. Those are the two systems that homeostatically regulate pH. We're going to review the lungs next week, but basically at the lungs, if you change respiratory rate, you can change CO2 content. By changing CO2, you change hydrogen ions and pH. So we'll talk about that next week, okay? But changing your respiratory rate can make your CO2 levels go up or down. By making CO2 levels go up or down, you can make your pH go up or down or up, okay? We'll worry about that later. Let's look here, okay? So we're gonna say it like this. We're gonna say if. We're not gonna use that color, okay? We're gonna start real basic, and then we're gonna add one extra thing to it, which it'll still even be basic, but we're gonna start real simple and then add one more little simple thing in. If our pH, our blood pH, is low, and that's normally what we deal with, okay? Usually, we're not dealing with a higher pH because our cells produce more acids than they do bases, like lactic acid, for example. Our cells produce more acids than they do bases. So usually our pH is a little too low. Okay? So if our pH is too low, that means that it's less than 7.35. Okay? Now, if your pH is too low, we're going to say at the DCT, what are we going to do to try to fix this problem? Now, the way I always work through these kind of problems is I say, if my blood pH is too low, I always write up here, that means I have too many or too few free hydrogens floating around in my blood. If my pH is too low, do I have too many or too few hydrogens in my bloodstream?
Too many.
I have too many. And I literally do this every time I do one of these problems so that I don't confuse myself. And once I know this, then it becomes very simple what I do at the DCT. At the DCT, if I've got too many hydrogens, then will I want to reabsorb hydrogens or secrete hydrogens at the DCT? Secrete. So at the DCT, I'm going to increase hydrogen secretion. And by doing that, that means that I'll have less hydrogens in my blood. And if I have less hydrogens in my blood, then it means I'll have more hydrogens in my urine. And if I have less hydrogens in my blood, then that means my blood pH should start going up. Increase blood pH back to range, back to homeostasis. That also means that if this is normally what we're dealing with, then that means your urine tends to be slightly basic or slightly acidic. If you have more hydrogens in your urine, is it going to be a bit more acidic or a bit more basic? It's more acidic. Your urine typically, so pH of your urine is typically around a 6 point something, okay? It can go to like a 4.2, I think, something like that, okay? But usually it's around like a 6 or so, something like that, 6.2, 6.3. And again, it doesn't really matter because it's all about keeping your blood in homeostatic range, not trying to keep urine in homeostatic range, okay? But this is usually what you're dealing with. So if we know that to be true, then we can do the opposite, right? So if your blood pH is too high, which it rarely is. But if it were, that would mean that it's greater than 7.45. And again, then I always write out here, I say that means I have too few free hydrogens floating around. So then at the DCT, I would want to increase hydrogen 1. If I have too few in my blood, I want to do reabsorption. I want to put hydrogens back in my blood. I'm going to increase hydrogens, reabsorption of hydrogens. And by doing that, my hydrogens in my blood will go up, which means that my blood pH will come back down to range. And if my blood was initially too basic, then that's going to result in my urine having less hydrogens. And my urine will end up becoming slightly basic so that my blood can get those hydrogen ions. Now, there's one more thing we have to add to this story though. And that is, when you look at the mechanism that transports hydrogen, we're gonna see that whatever we do to hydrogen, we have to do the opposite to bicarbonate ion. Now, bicarbonate ion doesn't mean very much to you guys right now, but it will next week. Okay, you'll see the significance of bicarbonate ions. We'll talk quite a bit about bicarbonate ions. But for right now, we're just gonna say whatever you do to hydrogen, you're gonna do the opposite to bicarb. That's just the way the transporting works. Okay? So, let's come back in here. So if blood pH was too low, which it typically is, that means that we're going to increase hydrogen secretion, which then means that we will increase bicarbonate ion reabsorption. And you'll see why that's actually a beneficial thing to do, okay? We'll talk about this next week, but this is typically what we do, this right here. Typically, our blood pH is too low, so typically at the DCT, we secrete hydrogens and we reabsorb bicarbonates. And that's beneficial for multiple reasons that we'll learn about next week. We come down here. If our blood pH is too high, which it rarely is, but if it were, we would increase hydrogen reabsorption at the DCT. At the same time, we would increase bicarbonate ion secretion. Okay, and you can follow this idea through too. So if we are reabsorbing more bicarbonate, then that means that we'll have more bicarbonate in the blood, and we'll have less bicarbonate in the urine. And then down here we have just the opposite. If we're secreting more bicarbonate here, then that means we'll have less bicarb in our blood, which means that we'll have more bicarb in the urine. Now, I'm going to say a couple things about that decreased aldosterone in the urine. Questions on that before I do that? Now, I want to just kind of clarify what's going on here on this slide. So this right here is just saying that in certain physiological states, you can see that blood pH can start to fall pretty quickly. And as it starts to fall pretty quickly, you're gonna see even more secreting happening at the DCT, just as you would expect. If your blood pH is starting to become too low, then you're gonna be secreting more hydrogens at the DCT. And this is just saying, what kind of situations might see that accelerated? So for example, if you're doing really intense muscular activity, where you're doing anaerobic metabolism, so you're working at near or at max intensity, like sprinting, or lifting something really heavy, you can't take in enough oxygen fast enough. And so your cells switch to anaerobic metabolism. As part of anaerobic metabolism, you produce lactic acid. And as you produce lactic acid, that's an acid. It's gonna cause your blood pH to become more acidic. And again, this is what you're gonna see happening at the DCT. Next week, we are gonna talk about this kind of thing a little bit. And if you really don't remember at all aerobic versus anaerobic, and why a muscle cell would do one versus the other, it may not hurt just to do, a 15-minute look that up, okay? So focus on muscle cells. Basically, aerobic, you're gonna use, well, I'm not gonna do it now because we're still a little more time, but I can talk to you about it later if you're blanking on that stuff. If you go to, if you just Google S-Morphield, the very first link that pops up is my old Google website. If you look under 241 and go to muscles, part C, there'll be a couple slides that explain that very easily, okay? It may not be a bad idea to do that if you're just totally, I don't remember any of that stuff. If you're in a starvation situation or uncontrolled diabetes mellitus, this goes back to hormones. So let's say a couple things about this, because that will also be relevant for your case study. Okay? So if you have uncontrolled diabetes mellitus, let's think about that for a second. If you have uncontrolled diabetes mellitus, and that means that for whatever reason, these are your cells. You've got a lot of glucose out here, and you can't get that glucose into your cells. Okay? So it could be that your beta pancreatic cells just aren't making the insulin. That would be type 1 diabetes. Type 1 is where you can't make insulin, we'll just say properly. And that's due to death of your beta pancreatic cells. They're not all dead, but they die off. Or you can have type 2 diabetes. Type 2 is where you make insulin just fine. No problem making the insulin. Here the problem is that your insulin receptors aren't working. Insulin receptors have either downregulated, so you don't have enough of them, or they're not working properly. But your insulin levels are fine. And the end result is basically the same, and that is that you've got all this glucose in your blood. That glucose diffuses out of your bloodstream into your interstitial fluids, and then you can't get it into your cells. Now, the problem with something like this is your cells like to use glucose to make ATP. It's easy to use glucose to make ATP. But these cells don't have access to that glucose. So essentially what happens is these cells, I'm gonna put this in quotes, think that you're starving them, right? They don't know that there's all this glucose out there. All they know is that they don't have access to it. And that's gonna cause hormones to start being released The same hormones will be released in uncontrolled diabetes mellitus as if you were actually starving yourself. The net effect is kind of the same, right? You've got all this glucose in here, but your cells are starving. So the same hormones get released. Things like cortisol, things like glucagon get released. And what do these hormones do? They try to increase glucose, right? They cause more glucose to be produced. With type 1 diabetes mellitus, you might be able to get some glucose into your, with both of these, you might be able to get some glucose into your cells. But it basically starts this chain reaction that's a horrible kind of catch-22, and that you keep making glucose, but you can't use that glucose, it just sits out here. And then the problem with it sitting out here is that it's gonna cause this environment out here to be very hypertonic, and that's gonna cause your cells to start losing water. So that's a big problem. When you look at your kidneys, you've got this filtrate now. Let's say you're at the PCT, the loop of Henle, DCT, collecting duct, and you've got all this glucose in your filtrate, right? You've got all that glucose in your filtrate, and it shouldn't be there. That glucose should be in your bloodstream and not in your filtrate. And with all that glucose in your filtrate, it's gonna ultimately end up where? In your urine. And the way they used to test for diabetes mellitus way back in the day was they would taste urine. And if your urine was sweet, then they knew you had glucose in your urine and you had diabetes mellitus. Fortunately, they don't have to do that anymore, right? But that's how they used to confirm diabetes back in the day. They would test how sweet your urine is.
Who confirms that?
People got paid.
The
to do
lab
that.
tech would do that, or the doctor would do it back in the day, right? Probably not, probably the nurse did it, is probably who did it. Right, probably the nurse. So, but the problem with this is, water's gonna follow that, right? And so water's gonna do this, and one sign of diabetes mellitus is your urine output becomes really high, because all that glucose in there is causing the water to end up in the filtrate. And so now your urine output's high. And so that's a key thing to look for with diabetes mellitus. You urinate a lot. Okay. Now, back to all this pH stuff. While doing all this, whenever you release cortisol or glucagon and you're making glucose, what did I say? You also will always do something called glucose sparing, right? At the same time, you're also gonna take adipose tissue, take those stored triglycerides, and break them down into fatty acids. And you do that because then at least the fatty acids can get into your cells, and not all cells can do this, but many cells can use the fatty acids to make ATP. But in the process, you produce a byproduct called ketones. And ketones are acidic. So this is a really dangerous thing that can happen with uncontrolled diabetes mellitus. Anorexics get this all the time. They go into ketoacidosis and they stay in that for a long period of time. And all those ketones can make your pH start to become really low. Now, diets are very popular nowadays, right? These ketoacidotic diets are popular because when you are producing ketones, that means you're breaking down fats. The problem is you have to be very careful. That can get dangerous really quickly. If you stay in that state too long, that can be dangerous. Yes, you're breaking down fats, but you're also producing a lot of acids in the process. Okay. All right, one last thing I'm gonna say about this excessive aldosterone thing, right? So we had said before that if you have excessive aldosterone release, which will not normally happen, we're gonna say you've got a tumor on your adrenal gland. So let's say not only is it excessive, but now it's going on for a long time, okay? So you've got all this aldosterone in your bloodstream, It's causing way too many potassiums to be secreted. Your blood potassium levels are getting lower, 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 lower. You have hypokalemia. That's dangerous. Second reason this becomes really dangerous is aldosterone's job is to not to regulate pH. It has nothing to do with pH. However, when you have excessive and prolonged aldosterone, what will start to happen now is, remember, aldosterone causes sodium potassium pumps to be made. Sodium you're going to keep reabsorbing, but now you've gotten rid of so much potassium, you hardly have any potassium to bind to these pumps to be secreted. So now what starts happening is hydrogen ions start binding to the potassium site on the pump. They should never be binding there. But if your potassium levels are so low, hydrogens will actually start binding in place of potassiums. And now what starts to happen? These pumps, let's get rid of this. You've got sodium that's getting reabsorbed, okay, that's still gonna happen. You've got potassium that was being secreted, but now because it's gone on for so long, you have so little potassium in your bloodstream that hydrogens start binding at the potassium site. And so now what you start doing is now you start, and you should never be doing this, you start secreting hydrogens with this pump that has nothing to do with hydrogens. Okay? So now this pump, you don't want to worry about that, but this pump starts secreting a bunch of hydrogens. And as this pump starts secreting a bunch of hydrogens, now the problem is you start to have very low hydrogens in your bloodstream. And if your blood hydrogen content starts to get too low, that's going to cause your blood pH to get too what? Too high, right? Too high. So, hey, what happened? It said time to go. That's what it said. It said time to go. Okay. All right. I take the hint. All right. Let me just say one last thing. So, aldosterone's job is not to regulate pH. It doesn't. Okay. Only if you have excessive prolonged aldosterone, not only can you end up with hypokalemia, but you can also end up in an alkalotic state that can be dangerous. Okay. All right. There's 2 slides left. We'll do those on Monday, okay? If you want to go up to lab, I will gladly go up to lab and open it up. If you don't, I totally understand.